I'm Ron Cochran, reporter and news analyst. The story I'm about to report to you certainly merits comment and requires analysis to understand its full significance. Like many a good story, this one did not begin with blaring headlines. It first came to my attention through a short press release. Possum Trot, Kentucky. That's right, Possum Trot. Groundbreaking ceremonies took place today for the building which will house the world's first aircraft jet gas turbine to furnish stationary power. Initial use of this jet power unit will be for transmitting natural gas through pipelines. Not very imposing when you first look at it, but I've been a reporter too long not to realize that here could be an important story. To begin with, a world's first is always news, so that alone seemed worth looking into. And then I wondered why a new type of power unit was needed for moving natural gas. And lastly, I wanted to find out if there really was such a place as Possum Trot. Well, I found all those answers and a few more, and I've put them together into a story I call The Constant Search. The search is for progress, for better and more economical ways of doing things. The searchers are 3 American companies who pooled their know-how and resources to bring the world this scientific first, the jet-driven gas turbine supplying stationary power. But a power package, no matter how new in concept and design, is only a scientific curiosity until it is put to work for a useful purpose. And the purpose existed in the never-ending search by natural gas systems for ways of improving methods of providing natural gas service to millions of customers. The Columbia gas system is today the nation's largest integrated natural gas utility. It serves homes, businesses, and industries throughout 7 states in the nation's industrial heartland. Its network of transmission and distribution lines spread from New York to Pennsylvania, Ohio, and West Virginia, into Virginia, Kentucky, and south to the Louisiana Gulf Coast. Now, to operate this complex natural gas system and supply both large and small users with constant and economical service requires investment of millions of dollars in equipment and construction of gas-delivering facilities. For every step in the discovery and movement of natural gas involves tremendous expense. And because natural gas is considered an ideal fuel to serve home and industry, new sources of supply must constantly be found. And when you think you've found a likely spot, there's really no sure way of knowing until you put up your rig, drill down 2, 3, 5, or even 15,000 feet, and come up with natural gas or a dry hole. But those are the chances you have to take when you're a company with 3 million households depending on you. So to keep pace with the ever-growing demands for natural gas, no place is considered too remote for exploration and actual drilling. But finding the gas is only part of the job. Getting it to where it's needed can be an even bigger challenge to men and machines. It takes big machines and tough, skilled, and determined pipeliners to meet this challenge. But meet it they do as they conquer mountains, swamps, and mighty rivers. And then at intervals along the pipeline, powerful compressor stations must be built and maintained to move the natural gas to its final destination. And distributing the gas to thousands of customers in villages, towns, and cities becomes a complex and intricate science of its own. In all of its operations, from exploration to distribution, the Columbia gas system constantly explores every scientific advance which would help to provide more efficient and economical service. A telemetering system provides a dispatcher with instantaneous remote control over dozens of regulators and valves. A pipeline analyzer solves distribution problems in half the time of ordinary calculating methods. And the latest electronic machines compute and make out 150 customer bills each minute. But it's in the field, on the transmission lines, and in the big, expensive engine-powered compressor stations where new and fresh scientific departures might provide for great advances in system efficiency and economy. This would be the case with an efficient, dependable engine that was simpler, smaller, lighter, and far more compact than the existing gas turbines and reciprocating engines used throughout the industry. Compared with these massive giants, Such an engine would cost less to build, transport, install, house, and operate. It might also reduce the costly, prolonged downtime of periodic overhauls. There are 146 compressor stations spread along the transmission lines of the Columbia gas system, representing a value of $107 million. If a lighter, more compact, more economical compressor unit could be found, well, you need to be neither scientist nor economist to see the many advantages such a unit would bring. If an answer could be found, it would be one more step in the constant search for more economical operating means, while also improving efficiency in delivery of natural gas to the consumer. But as I told you in the beginning of this report, there were 3 major American companies involved in this scientific achievement, for it's a characteristic of American industry, one of the elements which has made our nation the industrial giant it is, that if there is a need, a problem to be solved, or a new frontier to be explored, you can be sure that more than one company will be hard at work searching, experimenting, and researching to find the right solution. One such company is the Cooper Bessemer Corporation of Mount Vernon, Ohio, long established as a leading manufacturer in the heavy-duty engine and compressor industry. The management of the company realized some years ago that only by a new concept of design could gas turbines offer revolutionary advantages in industrial power. And they undertook to do something about it, not only to serve pipelines, but the related oil and petrochemical industries as well. Existing gas turbines with their massive heavy castings present not only weight, size, and foundation problems, with some heat stress problems too, but in order to approach acceptable efficiency, they must rely on regeneration. This means extensive equipment and components for circulating hot exhaust gases to capture heat energy otherwise wasted. This, of course, only adds further complications to the problems of size, weight, installation, piping, housing, and maintenance. Merely to build another Goliath that might outperform the competition was not the solution as envisioned by the progressive management of Cooper Bessemer. Just how the solution appeared and to whom is no longer a mystery. The idea was born in a small town in Ohio and carefully nurtured there behind the locked doors of the Cooper Bessemer Research Laboratory. And as with most original thoughts, the basic concept was of the utmost simplicity. Why not, the director of engineering reasoned, make use of an existing heat energy generator, one that had ideal qualifications and a proven record of performance, and of necessity was compact and relatively light in weight. And that's how the search led to the 3rd major company in our story, the Pratt and Whitney Aircraft Division of the United Aircraft Corporation, the world's leading designer and manufacturer of jet engines. In today's jet age, that company's jet engines power most of our armed forces' planes, interceptors, long-range bombers, and tankers, as well as the world-renowned Boeing and Douglas jetliners. Both of these sky giants are powered by Pratt and Whitney aircraft jet engines, power plants which have achieved more than 9 million flight hours. Here, then, was the answer to the power problem. The Pratt and Whitney aircraft J57 engine. Tremendous power in a compact package, plus the advantages of a proven design and skilled production facilities. The big question, of course, was, could an aircraft engine be used to perform a heavy industrial job, such as driving a compressor on a gas pipeline 24 hours a day for months on end? The leading engineers of Cooper Bessemer and Pratt and Whitney aircraft thought it could. And certainly the principle appeared sound, for basically a jet aircraft engine and an industrial gas turbine function in much the same way. Let me see if I can illustrate it simply with this toy balloon. When the stem is held or tied tightly to prevent air from escaping, the compressed air in the balloon exerts equal pressure on all sides. There is no action. But remove the string from around the stem, and away it goes. That's because the pressure on the whole side of the balloon is stronger than the pressure on the stem side through which the air is escaping. The action of the released air produces the reaction which drives the balloon in the opposite direction, thus pushing the balloon forward. The balloon flight is short because the pressure within the skin is quickly exhausted. Now, this problem could be overcome by pumping additional air into the balloon so that the pressure and air flows are reestablished and maintained. This is jet propulsion, the same jet propulsion which drives a full-scale axial flow jet engine. A compressor in the forward section draws the air in and delivers highly compressed air to the burner section, where fuel is sprayed into the compressed air. The fuel and air mixture is then burned to produce high-velocity gases that ram against the blades of the turbine. This blast turns the turbine, which rotates the compressor on the same shaft. After leaving the turbine, the remaining gaseous energy is forced through the exhaust nozzle at tremendous speeds. These reacting air pressures thrust the airplane forward, just as the action of the released air in the balloon produced the reaction which thrusts the balloon forward. To adapt an aircraft engine to industrial use, an additional turbine is needed. And let's think of this pinwheel as that turbine. Inserted in the jet flow, it absorbs the full potential of the jet thrust, like this. Now, this turbine, in turn, would power the compressor which moves the gas through the pipelines. And that, in principle, was to be the concept of this new kind of industrial gas turbine. But what looks good on paper and with toys doesn't always work out in practice. And yet, as every inspired American inventor knows, there is only one way to be really sure, and that's to go ahead and build it and make sure that it works. And that's exactly what the engineering teams proceeded to do. Pratt and Whitney aircraft engineers tackled the problem of converting the J-57 engine from liquid fuel consumption to burning natural gas. In this way, fuel from the engine could be tapped from the very transmission line along which it was helping to move the gas. At the same time, Cooper Bessemer engineers went to work on a special power turbine that could absorb the tremendous thrust of the J-57 and convert it to 10,500 rotative horsepower. In both aspects of development, there was complete collaboration and exchange of ideas between the two companies. Engineers from both companies were confident that the concept was sound and would prove itself in a practical field application. With this in mind, they approached the management of a Columbia Gas Systems subsidiary, the Columbia Gulf Transmission Company, with pipelines running from near Ashland, Kentucky to Rayne, Louisiana. For Columbia Gulf immediately saw in this power concept an opportunity for greater efficiency in compressor station operations. Not only were cost savings a definite prospect, but the entire power unit would lend itself ideally to remote automatic control. And so the partners in that constant search were drawn even closer together. Plans soon were completed and permission granted by the federal government for construction of a prototype compressor station on the grounds of an existing station here near Clementsville, Kentucky. After groundbreaking ceremonies attended by leading officials from all three participating companies, construction of the new prototype station quickly took shape. And because of the new turbine's basic simplicity, a completely remote-controlled operation would be possible. For compactness, efficiency, and construction design, the new station promised to set new standards for the entire industry. Shortly afterward, the new power turbine left the Cooper Bessemer plant and was moved to the Pratt and Whitney Aircraft Will-Goose Laboratory, the world's largest privately owned turbine testing facility. Here, turbine and jet engine were brought together for the first time and subjected to a long schedule of intensive tests which probed every aspect of both engine and turbine performance. These tests supported the conviction that because the aircraft engine is free from takeoff speeds, temperatures, and stresses, free from the extremes of weather and other flying conditions, a year's continuous operation could be expected. As the new station took more definite shape, each basic component was delivered and installed. The large centrifugal compressor that actually compresses the gas and speeds it on its way through the pipelines, the specially designed power turbine, and finally, the modified jet engine itself, combined with the power turbine to comprise a revolutionary industrial gas turbine known as the Cooper Bessemer RT-248. Auxiliary equipment, including safety controls and a complex of remote control and automation instruments were added to the finished power unit. And then, almost as though it were an everyday accomplishment, a simple flip of a switch. And a new era of industrial power had begun. The new concept in stationary power you've just seen in operation was once only a germ of an idea in the minds of a few forward-looking engineers. But through constant search and scientific study and outstanding cooperation among the three participating companies, the promised benefits of this new concept have moved from the drawing board and the shop to become working reality. And speaking of reality, here are some of the solid advantages. Total weight for the 10,500 horsepower jet gas turbine is only 34,000 pounds, compared with about 200,000 pounds for any existing regenerated gas turbine of comparable power. And since it's housed in a building about half the size otherwise needed, with far less foundation, piping, and crane requirements, Columbia Gulf estimates a complete compressor station at less than half the usual cost. And as for maintenance, the entire jet gas generator can be removed, inspected, and replaced, ready for operation in about 4 hours, compared with weeks of shutdown for other type gas turbines. And this new gas turbine, non-regenerated, approximately equals or exceeds the thermal efficiency of all other existing gas turbines. In its totally new approach to the problem of gas transmission, the Clementsville station will be watched not only by the pipeline industry, but all heavy American industry. For Clementsville is only the first example of what this new type of power can accomplish. Already being explored is the entire range of power applications based on aircraft jet power. 350 horsepower, 2,500, 7,000, up to 15,000 horsepower for the natural gas and petroleum industries, chemical and petrochemical services, for electrical power generation, for marine uses, wherever compact packages of power are needed. But that's another chapter in the story of the constant search. Oh yes, about that name, Possum Trot. It's there, all right. It's what the natives call a mountain ridge near Clementsville. I don't know why, but maybe I'll go back sometime and find out. Until then, this has been Ron Cochran reporting.